Hello, today we're going to talk about mixtures. So let's talk substances versus mixtures. Substances have the same composition all the way throughout. So like maybe it's the same compound or the same element. Those are substances. So let's make a little flow chart here. All matter can be separated into substances and mixtures. Substances are either elements or compounds. And remember, compounds can be ionic or covalent, so they could be called molecules, but they're all just one type of thing with distinct properties. Mixtures will have multiple elements or multiple compounds in them, and mixtures can be separated into heterogeneous and homogeneous. So a heterogeneous mixture, you can see the different parts. Think like trail mix or like a fruit salad. You can see the different items in a trail mix. Can you tell that I'm hungry? I'm using food examples. Homogeneous mixtures, you cannot see the different parts. A good one that I like to use for this is salt water. As long as the salt's completely dissolved, which it normally is, you cannot see the salt in the water, but like it tastes salty. But it's still a mixture of two things with distinct properties. Now, substances, if I wanted to break down a compound to an element, I would have to do a chemical reaction, or if I wanted to combine elements to make a compound, again, I would have to do a chemical reaction. Mixtures, you can separate the parts of a mixture using a physical change. So something like changing the state of matter. Like you can separate water from salt by boiling off the water. It's still water, it's just, as steam now. And then you could collect that water and turn it back into a liquid separately. That's called distillation. So substances are elements and compounds, same composition all the way through. Mixtures have different substances within them, and you can separate the substances within a mixture by using a physical change. So let's talk about some different ways you can separate mixtures. An easy one would just be filtration. So if you have a mixture where some particles are much larger than other particles, you can filter it. You use filter paper in a funnel, or you can use like if you're at the beach and you want to find seashells, you can filter through the sand, water, and salt water through the filter and keep the seashells on top. So it's filtration. Another method to use would be distillation. And distillation separates based on boiling points. So like I was talking about with salt water, you could boil off the water. That'd be distilling the water. So if you boil the water and collect it, it's distilled water. It leaves behind any of the impurities or like salt if you're doing salt water. You could also separate two liquids using distillation. So whichever one has a lower boiling point will boil off first, as long as you're heating it up slowly. Lower boiling point will boil off first, and it will leave behind the liquid with the higher boiling point. Another type of separation of mixtures is chromatography. Chromatography is a way that we can separate based on attractions of the substances within a mixture to a solvent. Typically, you'll see something like there's a piece of paper in a liquid, and the liquid just kind of sitting at the bottom, and when the liquid is drawn up the paper, whatever substance it runs through, some of those substances will move farther up if they're more attracted, and some of those will only move a little distance if they're less attracted. And that's chromatography. You can also do more simple methods of separation, like if you have a trail mix, you could pick out all of the almonds if you're allergic, like I am. So you just like a simple physical separation. You could use magnetism if, let's say you have iron in a sample or another magnetic element, you could pull out whatever is magnetic from things that are not magnetic. You could use melting point as a way to separate if you're doing solids instead of distillation. So there's a lot of different ways, but they're all physical changes. Now I want to do just a brief introduction to some reaction stoichiometry because we used chemical reactions earlier in the year to help us analyze mixtures, even though we won't really talk about reactions until Unit 4. But the basic idea is you have reactants changing into products, and they always react in a particular ratio. So let's say, for example, we have, let's do something like aluminum reacting with oxygen to produce aluminum oxide. And in a chemical reaction like this, the elements are staying the same on both sides. So the atoms are not changing into new atoms, but they are rearranging. So in this case, you have two separate elements coming together to form a compound, and you have to make sure that the reaction is balanced. This one, as I've written it, is not balanced because you can't make atoms disappear. So you have two oxygens turning into three oxygens. That doesn't work. So if I balance it, I add coefficients. I can put a 2 in front here and a 3 in front here, so now I have 6 oxygen atoms, and then I have 4 aluminum atoms to match the 4 aluminum atoms here. So now it's balanced. The elements cannot change on either side, but how they are arranged will change. So once you have a balanced chemical equation, you can use the coefficients to help you convert between amounts of reactants or products. So let's say, for example, you have 6.5 moles of oxygen gas. I want to find out if I use up all 6.5 moles of oxygen gas, how many moles of aluminum oxide will be formed? Well, I can use the coefficients because it reacts in a 3:2 ratio. There are 3 oxygen atoms, or 3 oxygen molecules react for every 2 aluminum oxide that is formed. So to solve for that, I would do 6.5 times 2 divided by 3, and you get 4.33 moles of the aluminum oxide formed. Now you can cancel out the oxygen in this case, and you're left with moles of aluminum oxide. You can also go ahead, because we're dealing with moles here, we can use this with grams and Avogadro's number that we've done before. So we can, let's say we have, let's see, 1.8 grams of aluminum. And I want to know how many grams of oxygen, how many molecules of oxygen it will take to completely react this. Let's do that one. How many molecules of oxygen? So the first thing to do is you change it to moles of aluminum. Aluminum's mass is 27. So grams per mole. So grams cancel. If I stop there, I'd have moles of aluminum. And then I know that the aluminum and the oxygen react in a 4:3 ratio. 4 aluminums for every 3 oxygen molecules. So that aluminums will cancel out there. And if I want to find out, I could stop there, have moles of oxygen, but if I want to know the molecules of oxygen, I can use Avogadro's number, which is 6.022 times 10 to the 23rd. That's how many molecules are in 1 mole. Moles on the bottom then cancel. And so to solve for this, you would do the 1.8 divided by 27 times 3 divided by 4 times 6.022 times 10 to the 23rd. And you get there 3.011 times 10 to the 22nd molecules of oxygen that it would take to completely react with those 1.8 grams of aluminum. So really we're just adding on the coefficient piece, or what we call the mole ratio, on to section 1, which was mole conversions. Okay, so now that we've talked about using balanced chemical equations, we can react part of a mixture to help determine the percent composition of that mixture. Let me give you an example. Let's say you have 10 grams of what you think is just baking soda. Baking soda is sodium hydrogen carbonate. But you know that it is contaminated with some kind of impurity. So that 10-gram sample has some baking soda and some other stuff in it. Usually they will tell you it's an inert impurity. Inert means it's not reactive. It's not going to react, but the baking soda will react. So that's kind of our way in to determine the composition of this mixture. Sodium hydrogen carbonate reacts, if we react 2 of the baking soda molecules, you can decompose it to form sodium carbonate, Na2CO3, and water and carbon dioxide. So let's say we perform that reaction and the water becomes a liquid, right? Carbon dioxide is a gas, but the sodium carbonate is a solid. So once you perform the reaction of the 10 grams of this mixture, you're forming some solid, liquid, and a gas. You isolate just the solid sodium carbonate, and you find that its mass is 4.20 grams. Maybe you filter the Na2CO3 from the liquid water. The gaseous CO2 just bubbles away. What we can do now is we can figure out how much of the sodium hydrogen carbonate you must have had at the beginning based on how much solid Na2CO3 we have left over. As always, we need to go ahead and use the molar mass of the Na2CO3 to change that to moles first. The molar mass of Na2CO3 is 106.2 grams per mole, grams on the bottom, and then I can use the mole ratio. For every 1 of the Na2CO3 that is produced, I use up 2 of the NaHCO3. That's the coefficients here. And even though the one's not written, it's still there. So the Na2CO3 cancels out, and we're left with moles of the NaHCO3. So let's go ahead and do that really quick. 4.2 divided by the 106.2 times 2. That means I have 0.0791 moles of the NaHCO3. And let's go ahead and convert this back into grams using the molar mass of the NaHCO3. Its molar mass is 84.1 grams per mole. Now you could do this all in one line. I just ran out of space. Moles cancel, and then we can multiply to find the mass. So the mass there is 6.65 grams of NaHCO3. So that means of the 10-gram sample, 6.65 grams of that must be baking soda based on how much of our product we have left over. And from there you could find a percent purity of that mixture. So if I take the 6.65 grams of the sodium hydrogen carbonate over the 10 grams of the mixture, and you should always label this NaHCO3, and then times 100 because it's a percent, and you get that the mixture must be 66.5% baking soda or percent sodium hydrogen carbonate, which means that the other 30-some% must be the impurity.